let's take a look at number 20. This is another example of a hypothesis testing for two means with independent samples where sigma 1 and sigma 2 are unknown. Okay, so here, this is a situation where I've got two samples and I have the raw data. Okay, so here's the situation. An engineer wants to compare the tensile strengths of steel bars that are produced using a conventional method and an experimental method. To do so, the engineer randomly selects steel bars that are manufactured using each method and records the tensile strengths listed below. At alpha equal 0.1, can the engineer support the claim that the experimental method produces steel with a greater mean tensile strength? Assume the population variances are not equal. Okay, so I first want to write the claim in terms of the parameters mu1 and mu2. Okay, so mu1 is going to represent the experimental method's population mean, and mu2 will be the conventional method's population mean. Okay, so the engineer claims that the experimental method, mu1, is greater than mu2. Okay, so this is the engineer's claim. Okay, so since this does not contain the case of equality, this is the alternative. So this makes the null hypothesis mu1 less than or equal to mu2. Okay, so again, I'm not going to be finding the test statistic by hand in this situation. You can go ahead and do that. Because we're told to assume the variances are not equal, that denominator is a little bit easier to work with in that test statistic formula. And again, in the real world, we would actually test for equivalency between the two variances before going ahead and doing this particular test. However, in this class, we're just going to be told whether or not to assume the variances are equal. Okay, so I need my standardized test statistic, which is a t-value. So previously, I went ahead and put the information into the calculator by pressing stat and then edit. Okay, so I put the experimental method in list 1 and the conventional method in list 2. Okay, so I want to go back to my stat menu, right arrow over to tests, and scroll down to the 2-sample t-test. Okay, so here we're not told to assume anything about either population standard deviations. We're basing everything off the sample. Okay, so because we're using the sample information inclusive of the sample standard deviations, this is going to be a t-test. Okay, so selecting 4. Now, in this situation, I don't have the summarized statistics for each method. Okay, if I did, I would have to highlight stats and then put in the information. Okay, so I'm going to keep it as data that's highlighted, and then I need to tell it where my data is. Okay, so I put my data in list 1 and list 2, and then after that I'm going to scroll down and change the direction of the alternative if I need to. Okay, so for this particular problem, it's an upper-tailed test. Okay, so I can go ahead and leave that. Now, we're told in the problem to assume that the variances are not equal. Okay, so I do not want to pull the variances here. Okay, so after selecting no, I'm going to press calculate. Okay, so here's our test statistic. It's about 3.429, okay, with a corresponding p-value of about 0.0012. Okay, so let's go ahead and take a minute to interpret the decision in terms of the p-value. Okay, we're told to use a level of significance of alpha equal 0.1. Okay, so I'm going to compare my p-value to alpha equal 0.10. Okay, so my p-value is 0.0012. Okay, my level of significance is 0.1. Okay, the p-value is less than or equal to my level of significance, so I'm going to reject the null. Okay, so this is a pretty small p-value. Okay, there is strong evidence in support of the alternative. I would be rejecting the null at alpha equal 0.05 and also at alpha equal 0.01. Okay, so this test statistic is not going to be close to the critical value. Okay, and we'll see that once we find it. Okay, so at this point in time, my decision is to reject the null. Okay, so if I'm rejecting the null, I'm in favor of the alternative. Being in favor of the alternative when the alternative is the engineer's claim means that there is sufficient evidence to support the engineer's claim, okay, that the experimental method produces steel with a greater mean tensile strength. Okay, so let's go ahead and find the critical value. Okay, so we're going to need our degrees of freedom. Okay, now the method that the book uses is we need to use the smaller degrees of freedom. Okay, so we've got two samples here. Okay, my sample sizes were 17 and 14. So I want to choose the smaller degrees of freedom. Okay, so I'm going to go with a degrees of freedom equal to 13. Okay, so in this particular problem, the degrees of freedom will be equal to 13. Now you may notice in your calculator that it outputs fractional degrees of freedom here, and that can happen. Okay, the reason why that happens is beyond the scope of this course. Please don't use this degrees of freedom because the method in the book wants us to select the smaller degrees of freedom. That's actually considered the more conservative case. Okay, but if we were to use this degrees of freedom, this is based on something called Welch's t-test. We would take the integer portion, so we would use 21 degrees of freedom. Okay, but that's not consistent with an introductory statistics course, and so we're going to go ahead and use the method that is outlined in the book, which actually helps protect against a type 1 error. Okay, it's a more conservative estimate of a critical value. It's going to give us one a little bit further out in the tail than using this degrees of freedom. Okay, so using a 13 degrees of freedom, and this is an upper tail test. Okay, that's a terrible bell curve. I apologize for that. Okay, I want 0.1 amount of area in this upper tail. Okay, so looking at my t-table, I want to read down to 10 degrees of freedom and over to 0.1 area, amount of area in one tail. So what's my degrees of freedom again? I forgot. Okay, that's 13. Okay, so I have a critical value of 1.35. Okay. So taking a look at my standardized test statistic, I'm way out in this tail. Okay, T star is way out here in that tail. Okay, and I expected that to happen because my p-value was really small. Okay, this is significantly lower than an area of 0.1. Okay, so remember the p-value represents this little bitty area from our our test statistic to positive infinity. Again, if you wanted to find the critical value using your inverse t in your calculator, if you have that, that's perfectly acceptable. You just want to make sure that you put a cumulative area of 0.9 for your input. Okay, so our decision is to reject the null and support the engineer's claim. Because we're rejecting the null hypothesis, it is possible that a type 1 error may have occurred. Okay, so we're going to reject the null hypothesis and conclude that there is sufficient evidence to support the engineer's claim and also a type 1 error may have occurred. It does not mean that it absolutely did occur. It just means that because we're basing our decision on a sample, and samples have an inherent error built in, it is possible we came to this conclusion by mistake, but setting our level of significance fairly low protects us against that risk. Okay, last but not least, let's take a quick look at the confidence interval. Okay, since my level of significance was 0.1, I want to find a 90% confidence interval for mu1 minus mu2. Okay, so again, this is a built-in function in the calculator. I'm going to press stat, right arrow over to test, and then I want the 2-sample t-interval. Okay, so you scroll down to find that. And it should carry over the information. I put my information in list 1 and list 2. I want to change my level of confidence to 0.9 since my level of significance is 0.1. And again, I don't want to pull the standard deviations for that denominator. I need to select no and then calculate. Okay, so the confidence interval limits from the calculator screen go from about 9.35 up to 28.18. Okay, so let's interpret that in context of the problem. If I were to move mu sub 2 over to the other side here in the hypothesis, I would have 0. Okay, so the null hypothesis would be that there is no difference between the two means. Okay, so an alternative version of this would be mu1 minus mu2 is less than or equal to 0. Again, it contains the case of equality, versus mu1 minus mu2 greater than 0. Okay, that difference is greater than 0, which would indicate that the overall mean for the experimental method is on average greater than the conventional method. So let's take a look at this confidence interval. This confidence interval does not contain 0. Which is the case of equality. Okay, so what that means is if this confidence interval did contain 0, I would be in favor of the null hypothesis. But this confidence interval is well above 0. Okay, it's not even close to 0. So we are strongly in favor of the alternative here.